All right. Welcome everyone to the string theory, string Pinot seminar series. Today we're very happy to have Vincent Van Hemelryck from Leuven, and he will tell us first about scale-separated AdS4 vacua of 2A orientifolds and M theory. Please, Vincent.
Thank you, and also thank you for allowing me to speak here. So I will speak particularly about work that I did with Niccolò Crediori, Daniel Junghans, my supervisor Thomas van Riet, and Tim Razen some months ago. And the main motivation for this work is actually something that we all observe. Doesn't matter where you are. It can be in the mountains, it can be in the nice city center of Leuven, or even while you're enjoying a concert, it doesn't really matter. And that observation is that our world is four-dimensional, or at least it seems to be four-dimensional. And for us string theorists, it's of course an interesting question how this observation can be reconciled with string theory. Because you know that string theory has extra dimensions. String theory is best understood in 10, and we typically want lower dimensional theories, not only for phenomenology, but also for other reasons. And to obtain lower dimensional effective field theories, we need to hide the extra dimensions. And for that, you have basically two options. The first one is to construct brane worlds. So these, then you actually confine the physics on a specific brane that lives on a brane that is embedded in a larger space. And typical examples of this is the so-called Randall-Sundrum scenario. But there are also other types of models constructed, especially by these people in Uppsala. And the other route, more explored route, I would say, is the route of flux compactification. So there you take your string theory and you compactify it on a compact manifold. You introduce fluxes and you hope that, well, you have a lower dimensional theory. And to obtain a genuine lower dimensional theory, you hope to obtain small extra dimensions. Now, what do I mean with small? Well, this is the so-called scale separation condition. So for scale separation, we just require the Kaluza-Klein length scale to be way smaller than the curvature scale of your external space. So in my talk, it will be mainly the AdS curvature scale. And so this KK length scale is just inversely proportional to the mass scale of a tower of states that you get after Kaluza-Klein reduction. So when this condition is met, only then you can speak of a genuine lower dimensional theory. So this is what we are going to talk about in this talk. And of course, the scale separation condition is nice, but we also want it with full moduli stabilization. And that is a bit harder than it just might seem. So actually, there are two classes of vacua that achieve this. And the first one are the so-called classical vacua. So there, all of the moduli are stabilized with classical ingredients. So then I'm thinking of fluxes, but also local objects like D-branes or orientifold planes. And the real benefit of these vacua is that you have parametric control. There is a parameter, typically a flux number, that you can tune to infinity. And with that, you gain infinite control, basically. It's like a large N expansion. Now, the prime example of such a vacuum or of such a class of solutions are the DGKT solutions in type 2A supergravity. So DGKT stands for the Wolf, Giriavet, Tatchell, and Taylor. This is for AdS4 vacua, but there are also AdS3 variants written down by my supervisor and his collaborators. So that's one class of solutions. On the other hand, you have what I would like to call the quantum vacua. And there you need more ingredients. You do not only need the classical ingredients, but you also need quantum ingredients to stabilize all of the moduli. And so examples of that could be alpha prime corrections, but also things like gaugino condensates on a stack of D7 branes, like in KKLT. There, in this type of vacua, you do not have the same parametric control. You don't have the full parametric control that you have in the classical case. And the prime examples there are the large volume scenario or KKLT-like models, and they're all set in type P. So yeah, so there actually it amounts to finding small W naught, and this is work for many people that many people in the audience as well have been doing. So I've only here cited the most recent ones that I could think of, but of course, it's many more. Now, of course, these two classes might achieve scale separation, but there is a lot of criticism against these scenarios. And I would say that the situation is a bit bad because people have actually also formalized their criticism in conjectures. For example, the AdS distance conjecture of a couple of years ago. So in order to understand whether these criticisms are justified, we need to do a more like thorough investigation of these type of examples. And in my talk, I will just focus on the classical vacua. And moreover, I will do that so in n=1 AdS4. And to do that, I will quickly summarize what these DGKT solutions are. So DGKT is set in massive type 2A. So that means that you have a non-zero zero-form flux, which is given by some mass parameter m. And so they obtain AdS4 vacua, but for that they need 4 sets of intersecting O6 planes. And they do so on an orbifolded 6 torus. So I've tried to depict that 6 torus here. So I factorized it in 3 2 tori, and every color here represents a different set of orientifold planes. So you can see that the green orientifold indeed intersects the black and the blue and the red in any of the tori. And so DGKT realizes full moduli stabilization with fluxes on this setup. And the fluxes are actually can be written down, or the solution can be written down in a rather simple way, because the solution is a manifold with SU3 structure, and then there are these nice formulas considered by these people here. And so you can see that all of the fluxes are determined by this parameter m. So m is here the Romans mass. And this m also determines the AdS curvature scale in this fashion. Now, what's really nice about this solution is that it has a scaling symmetry. So if I rescale all of the quantities in these equations with a parameter n to some power, then you will see that these equations remain invariant under this scaling symmetry. So this n is not just an arbitrary parameter, but it's really the 4-form flux in your compactification. So this 4-form flux really acts as a dial. So when I increase n, the solution changes, but it still remains a solution. But while n increases, the volumes of the 2 tori increases, the AdS curvature scale increases, you get weaker and weaker coupling, and of course, because n corresponds to the 4-form flux, it increases as well. But this all happens in a very particular way. So, and that particular way achieves us also scale separation, because the KK scale in this simple setup is just the volume scale, which scales like n to the 1/2. The AdS curvature scale scales like n to the 3/2. And so the ratio indeed goes to 0 for n large. So you achieve scale separation with an infinite amount of control. And with that, I just mean that you tune n as large as you like. Now that's all nice, but there has been some criticism formulated against this proposal because it uses 4 sets of intersecting O6 planes. And this is actually a configuration that we don't even understand in flat space. So we don't really know how you should make sense of that in the simplest case, really. Also, these O6 planes are smeared in this setup, but and that might be a worry to you because these O6 planes are local objects. They are codimension 3 in the 6 torus. So what if you should treat, well, you should treat them locally. You should treat them as local objects. And this has actually been done in a perturbative scheme by Daniel Junghans and also by Marchesano, Paltikira, and Tomasiello 1.5 years ago. So there it seems to be all well at first order in this perturbative scheme. And a second, third issue is that when you do this localization, you of course create profiles for warp factors and dilatons, and these profiles have singularities. And the singularities might worry you, especially because you have Romans mass, and this is why we'll explain now. So, and the reason why you might worry about it is the O6 back reaction, because, for example, for the dilaton, when you have this profile, typically it will blow up near the orientifold locations, and there you will have strong coupling. But this might help you because strong coupling, we know that in a strong coupling regime, type 2A supergravity is better described by M theory. So you can go to an M theory description. And we know that orientifold 6 planes lift to a sourceless but singular geometry in 11-dimensional M theory, and that quantum effects smooth out these singularities so that there are effectively no singularities left. This is a so-called Atiyah-Hitchin mechanism that has been studied in these papers. But all of these stories cannot go through when you have a non-zero Romans mass, because this only works for massless type 2A. So this game cannot be played for DGKT, and that's really a pity. Now, I must say that people have been trying to understand whether these singularities are okay or not in other fashions, and for that you would want to look to the papers by Tomasiello, Serraco, and De Luca, who have been studying this. As far as they have seen, well, it's not really completely understood whether these singularities are smoothed out or not. So the upshot of our work is that we try to circumvent this latter issue by going to massless type 2A. And the claim that I want to make about our paper is that we found weakly and strongly coupled solutions in massless type 2A, and that these strongly coupled solutions live to M theory, and that all of these solutions have scale separation. And I will show you now how this is realized. So for that, we need actually a secret ingredient, and that's a twisted 6 torus. So before in DGKT, the 6 torus was flat, so it was a flat metric. It was actually like Calabi-Yau, but for us, we will go away from that. So we will not have Calabi-Yau manifolds, but we still will look at manifolds that have this so-called SU3 structure, and more generally, now you have this other parameters, this M tilde, which appears also a lot, and also a torsion class W2. So with these, the scalar 2 form J and the holomorphic 3 form omega will not be closed anymore. So it means that the 6 torus indeed is twisted. It's not flat anymore. And this M tilde, again, is also determining the curvature scale. Now, I advocated to you that we want to go to massless type 2A, so we simply put this M to 0, and we are only left with this M tilde and this W2, so we don't have H flux anymore, we don't have F0 and F4, only F2 and F6, and of course a twisted torus here. And of course, I'm not only going to advocate it to you in this way, but we have a particular example, a particular realization of this, and that's a background on a solution on the so-called Iwasawa manifold. This is a nil manifold. It's not something new. It has been around for a long time and has been studied in these papers and many more. And so the whole solution can be seen as a twisted 6 torus or be folded by a Z2 cross Z2 group. And this whole solution can be seen as the double T dual of the flat case, so of the DGKT solution on a flat T6 or be followed by Z2 cross Z2. So the twist of the torus is realized in the sense that the one forms that are living on this first torus are not closed anymore. So they have these intricate relations here, whereas the other one forms on the other tori are still closed. And so maybe also important for later on is that these length scales LT, L2, and L3 determine the volume of these two cycles. So with this solution at hand, we could ask ourselves whether we again have such a dial, a scaling symmetry, with which we can achieve scale separation. And luckily we do, but this time the scalings are a little bit more intricate because we need to consider anisotropic scalings. So the scalings are written down here. So the upshot is that they're all determined by 3 scaling exponents, A, B, and C. And so A determines the scaling of the 6-form flux, whereas B and C determine the scalings of the 2-form fluxes along the 2 different tori that are not twisted. And so you see that A and B and C, well, they can be whatever they want, but they better be larger than 0 in order to have growing fluxes when you scale and up to infinity. Of course, there are also other constraints on A, B, and C if you want to have all of the volumes of these 3 tori large, and that I have shown in here. So this blue region shows you when you have growing fluxes and when all the cycles are large. But you can see that we have also a region where we have strong coupling, but also a region where we have weak coupling. But what's nice about it is that it doesn't matter what you have. We have scale separation in either way, because the KK scale in this case is given by the length scale of the largest torus, which is quite reasonable because that would give you the lowest KK mass. And when you compare that KK scale with the AdS curvature scale, you indeed see that it scales down to 0 when you increase. And so we achieve scale separation again. Now, a second worry that might appear to you is that the one of backreaction of the O6 plane. Not so maybe for the weakly coupled solutions, but more for the strongly coupled solutions. Because we know, for example, that when these things, when the dilaton gets a profile, then the distance from which strong coupling appears close to the orientifold plane arises at a distance around GS. And this distance GS is better not larger than the length scale of your compactification, because then the backreaction would be way too large. And so we've verified that GS divided by the appropriate length scale that measures this, which is a little bit intricate, but it's all safe and sound. Well, we see that indeed this is way smaller than 1 in the large n limit, so that the O6 backreaction is under control, and especially in the strongly coupled case. Now, I advocated to you that we want to uplift this solution to M theory, and we can do so because now we have a massless type 2A solution, and we can just use the standard formulas. But there is a problem arising when we do so, because naively, this approximation, well, the setup that we used, where we also used a smeared O6 planes, well, for that, the 7-dimensional curvature becomes negative because a nil manifold, the 6-dimensional nil manifold has negative curvature. But this 7-dimensional curvature needs to be positive because we claim to have a sourceless M theory geometry, a 7-dimensional geometry, and then it has been shown that this curvature needs to be positive. And I must say that setups like this, so a double T dual of DGKT, have been attempted before by Banks and Van den Broek 15 years ago, and they also tried to uplift it to M theory, but there they did something wrong. They also use the smeared approximation where they have this problem, but they also have shrinking cycles, which we don't want. And I want now to show you that we can fix this issue by making our solution local. So by treating these O6 planes as local objects. And to do so, we need to introduce new things, and that new thing is warping. That has been known already for a long time. The moment that you introduce local sources, you get warping. And the procedure that we are going to use to localize this solution is the same as the one that Daniel Junghans used for DGKT 1.5 years ago. So for that, we are going to make an expansion of all our ingredients. So yeah, we will do that, but we need something more, and these are mixed components of F2. So with that, I mean that now we will have components of F2 that have a lag along different tori. So for example, a component of F2 along this torus and along this one, whereas before we only had components of F2 wrapping only the whole torus. Of course, we will also have non-trivial warping and a non-trivial profile for the dilaton. And our expansion window will look like something like this. So I have illustrated it here for a component of F2. So the 0th order contribution in the expansion will just be from the smeared approximation. So the things that I showed to you before. And the 1st order contribution will encode the local information. As you can see here, I've introduced this small parameter n to the minus b, and this n to the minus b controls, as I showed before as well, the size of the back reaction of the O6 plane. So, and it's small, so we can do that expansion. And it seems that this parameter is indeed the right thing to use. So then
Vincent,
the whole,
you have about 5 more minutes.
Okay, that's fine. So of course, the localization in a perturbative scheme is quite easy. We make an expansion of the equations of motion and the F2 Bianchi identity and look at the lowest order contribution in this parameter n. We replace the 0th order terms in favor of the smeared sources, and then we just solve the equations for the 1st order terms. So very simply illustrated for the F2 Bianchi identity is, well, the Bianchi identity looks like this in a schematic way. I replace this F20 term by the smeared source. So this J is the smeared source, whereas delta is the local source. And then I end up with an equation like this. It's very trivial in this sense, but it gets less and less trivial or more complicated for the Einstein equations and dilaton equations of motion. But we play that game. And the thing is that when we solve the equations, it's quite easy. Well, it's relatively easy to do so when we consider a superposition of single source solutions. So we pretend that there is only one O6 plane, we solve the equations of motion, and then add solutions for different O6 planes together so that we have a solution for all of the O6 planes. And all of these 1st order local corrections are really taking part in an adoration of the mystic Poisson equation here. So all of these 1st order corrections, they are parameterized by a function beta, and this beta is just must satisfy this Poisson equation. So all of the equations of motion and the Bianchi identity reduced to this equation. So that's quite nice, and it's relatively easy to solve this one. And so then just the sum of all of these single source solutions gives you the total solution. Now then, when we have that solution, we do the uplift to M theory again. We notice that scale separation also in M theory holds, because the KK scale in M theory is still given by the length scale of the largest torus. So the M theory circle doesn't change much. And the back reaction corrections indeed cure this 7-dimensional curvature to be positive. So that's good. So we have a good uplift without any sources, but with singularities. And then the hope is that an Atiyah-Hitchin-like mechanism cures these singularities. But you might say, Vincent, did your supervisor not tell you a couple of years ago, together with his collaborators, that scale separation is forbidden in M theory? Because they showed that if the KK scale in M theory is measured by the curvature scale, then scale separation amounts to this ratio of integrated curvatures to be large. But they showed that for sourceless geometries, this ratio needs to be smaller than 5/4, so that scale separation cannot occur. But the loophole in this no-go theorem is that the KK scale and the curvature scale are not the same, they decouple. And so our solution still satisfies the scale separation condition that I showed to you before, but also satisfies this condition. So that's quite nice. So I will now conclude. So I showed you in this talk that we have constructed a solution or a class of solutions in massless type 2A that can either have weak or strong coupling, where all the cycles can be made large, and where scale separation can be achieved, and where the O6 backreaction is also under control when you have this scale separation. Then I uplifted these solutions to M theory. They are also scale separated. And the fact that we can even do that is thanks to the strong coupling that we have, and the fact that we have a local solution. And this local solution that we uplifted to M theory gives a sourceless solution in M theory, but still has singularities. And then the question is whether an Abdiahitsian-like mechanism can cure these singularities. So our local solution is also a linear superposition of single source solutions. So our O6, the O6 planes, they normally intersect, but this cannot be seen at first order in perturbation theory. So if you want to see these intersections, you might have to go to second order or beyond. These classes of solutions, they also violate the swampland conjectures, specifically the strong AdS distance conjecture. So the question is whether something might go wrong with this construction, maybe at the intersections that I've just been talking about, or this conjecture has to be refined, such as what the Madrid group has done with the discrete symmetry group refined strong distance conjecture. And then a last question that you might ask is what happens in type 2b in these classical vacua in type 2b with O5 planes and O7 planes, because we also have been looking at that, and we have not seen well, we have seen that there also we cannot achieve scale separation while maintaining large cycles or a small or weak coupling. So, and with that, I would like to thank you for your attention.
Thank you, Vincent. Thanks a lot for this excellent talk. So I see we have a few questions. I think, David, you were the first one to raise your hand, so please just ask away.
Hi, Vincent. Yeah, thanks a lot for the very, very nice talk. I just had a quick question. Can you remind me if in the original paper, I think of Zimpis and Kerber and Lust, where they had this solution, I vaguely recall that numerically they could indeed see there was scale separation. I'm wondering if in their solution it was massive or massless, or whether there was Romans mass or not, whether it's the same thing as you or not.
So, so indeed, Lust and Zimpis and Kerber, they and many more, they looked at this also at this Iwasawa manifold, but so in the original paper by Lust and Zimpis, they looked at sourceless solutions. So we have sources here, so that's a difference. And with so in the other paper of 2008 with Kerber and the other people, they did not do the scaling analysis. So I don't know. But what I can tell you is that this Iwasawa manifold can only be made consistent when you have massless type 2A. So,
but do you remember
if you still impose? Yeah. So there you don't have F0 if you still want to have this SU3 structure.
Okay, thank you very much.
Wadi, please.
Yeah, thanks. That was a nice talk and quite interesting stuff. Can you say a little bit more about the mechanism and extent of the separation of the KK and curvature scales?
Yes. So, well, let's see where I can go back. Yeah. Okay. So you mean here, right?
Yeah. The decoupling,
so, yeah.
Exactly. The
yeah.
decoupling.
So I haven't written it down here, but what is KK? So the KK scale here is our L2. So let me maybe go to this slide. So the KK scale is given by the largest length scale in our compactification. So it's this one, and the curvature scale for a nil manifold, when you have anisotropy, so when not all of the length scales are the same, it's not just 1 over the volume to the power 1/6 or so, but it's in this case it's actually L2 times L3 divided by LT. And so if you work it out, it does of course not scale the same as L2.
Great. And possibly even related to that, you commented that these are related by 2 T dualities.
Yes.
Yes. To the massive 2A cases. So the 2 T dualities presumably work on, like normally 2 T dualities would take something geometric to something non-geometric.
Yes. But yes,
you avoided that by taking a proper 2 T dualities or something?
Yes. So what we do is we perform 2 T dualities along the same torus. So you decompose the T6 into 3 tori, and you perform the T dualities along the same 2 torus. So in that sense, you don't generate non-geometric stuff, so only geometric stuff. So you have initially in the normal DGKT solutions, you have 4 H fluxes, and they get transformed into these 4 non-geometric fluxes that you can see here. If you imagine here
geometric,
1, 2, 3, geometric,
Before geometric, great. Okay, thanks very much. Nice talk, thanks.
Okay, thanks to Vincent again for this very nice presentation.